Okay, let's look at an example. This is example 5.1, but I'm going to modify a little bit. Now, example 5.1, it just asks you to draw a three-body diagram. But let's actually solve for something. Now we have a rigid body, and it's a metal bar that's glued to a wall this way. Okay. You apply a force, 1,200 newtons force, at this location, 2 meters from the wall. And this metal bar is 6 meters long. And the mass of the bar is 100 kilograms. Now, I'd like you to find all the reactions at point A. Okay, actually go through the calculation and find the reactions. It could be reaction forces as well as reaction moments. Okay, so let's use the solution steps, right, and go through that. So step 1 is define a coordinate system. Now this is obviously a two-dimensional problem. Okay, so x and y. So I'm going to just define my x this way, y goes up. Okay, that's conventional. Okay, that's conventional. You can define it separately. You can define it x going to the left if you like, or y goes down. It doesn't matter. Okay, as long as your math is consistent with how you define a coordinate system. Okay. Step 2, draw your free body diagram. So, free body diagram. Just draw the rigid body without a wall. Okay, do not draw any physical attachments. Right, so no wall here. Just the rigid body, and then you draw all the forces and a couple moments applied on the rigid body. So here, obviously, I have this applied force of 1,200 newtons. And I'm going to call it F1 for that. Here I have reaction, reaction forces. And since this is glued to the wall, so I'm constraining it in both directions, x and y direction. So at this point, okay, I'm resisting it, okay, in the x and y direction motion. Also, don't forget about the weight, right? So the mass is given. So the weight of this rigid body must be taken into account, and the weight is applied at the center of gravity. Okay? The center of gravity, so in this case, okay, this is a homogeneous piece of metal. So that's my assumption. Okay? So this means that the material, whatever it is, okay, has the same density everywhere. Right? So the center of gravity will be right in the middle. So that's where the weight is applied. Now weight is mg, which is 100 kilograms times gravitational acceleration, so that's 981 newtons. Okay, that's it. This is my free body diagram. So I have two reaction forces, applied force, and one weight, right, due to gravity. But is that it? Is that really all the forces? No. Keep in mind, rigid bodies has linear, okay, forces as well as rotational effect. So this rotational effect is moment. So do we have any moments here? Well, there's no applied couple moments. Okay, so we don't have that. But look at this kind of reaction, this kind of support. Right? It's glued, right? So I don't allow this rigid body to rotate at all. This means that this rigid body would resist, okay, the rotational tendency in the form of moment. So this is my moment reaction. Okay, call it M. Okay, so let's call it MA. Okay, so now it's complete. So I have 1, 2, 3, 4, 5 items. Okay, on the rigid body. Now, I want to point out that the direction of these two, the reaction forces, as well as this, the reaction moment at point A, the direction are assumed. I don't know actually whether this Rx points to the right. It could be pointing to the left. I don't know. Ry, again, it could be pointing to the downward in reality. But since they are the unknown, I cannot know beforehand. So therefore, I just have to assume a direction. So I just assume that this goes to the right and this goes up. Similarly for MA. I don't know that this actually goes counterclockwise. So that's my assumption. Okay? So directions are assumed. Okay, so this guy, and this guy. Okay, so now with the free body diagram in place, just apply the equation. Alright, so now we have equations. Since it's a 2D case, we have 3 equations. Sum of forces X, sum of forces Y, and sum of all the moments about any point. Once again, it doesn't matter any point. Okay? Now, this sum of forces, okay, since you're free to sum a moment, okay, it's your choice, okay, which point you choose to sum moment about. Okay? So I'm just going to call it point O for now. Okay? Which point you choose will have different consequences. Okay? If you choose a smart point, then your solution will be a lot easier. Okay? So let's consider this a little later. Okay, let's talk about the forces first. All right, so these 3 must be satisfied simultaneously. So equation 1 and 2 and 3. Okay, let's deal with forces. Get out of the way. So equation 1, sum of forces equal 0 in the x direction. Next, expand left-hand side by applying this equation to the entire free body diagram. So left-hand side, just look at all the forces in the x direction. So what do we have? We have our x in the x direction. Sure. What else? That's it. This is the only guy in the x direction. Therefore, our x equals 0. This doesn't exist at all. There is no x reaction force. Okay? So that's one of the unknowns I just solved for. Alright, move on. Equation 2, sum of forces y equals 0. Left-hand side, expand that, okay, by looking at the free body diagram. So point out all the forces in the y direction. I have Ry. Now, since I assume that this points up, so that's positive. What else? I got F1 minus F1, and then minus W. That's it. Alright, so there's no other forces vertically. Right hand side equals 0. Here, I have only one unknown, which is Ry. Equals, move the other 2 guys over, plug it in. F1 is 1200, W is 981, so that's 2181 Newton. That's it. And that's positive number. This means that positive means my assumption of the direction is correct. Therefore, Ry, yes, is indeed pointing upward. Okay? Alright, so I knocked 2 guys down. I need to find the last one. Is MA. What is MA? Well, let's apply the last equation. Okay? So, now first, By the way, you realize that we have three unknowns here, Rx, Ry, and Ma, and we have three equations. So three unknowns, three equations, mathematically, we're okay. Okay, so you can never have more unknowns than available equations. Okay, so let's look at this last equation. Sum of moment. So, which point are you going to sum moment about? You can choose any point along this rigid body or outside the rigid body. Doesn't matter. But keep in mind, moment, okay, equals R cross F. Okay, vector form. In terms of scalar, moment equals F times D. D is the perpendicular distance, the shortest distance, right, between whatever point you take moment about and the line of action of the force. So this means that if you take moment about, let's say, this end point right here, then I'll have to take into account this weight, okay, because this weight will generate a moment, right, about this point, right, and the distance is here. This F1 also have a second moment, okay, so it's F1 times this distance right here. Ry will also have a moment, okay, Ry times the entire length of the rigid body. That's another moment. Now, is there a point that I can choose where I can simplify a little bit, so I don't have to take into account all these forces? What if I choose a point where this D is 0? Okay, so whatever force that is, right? This D, the distance, okay, between the force and this point, is 0, which means this point that I choose to take moment about actually is on the line of action of the force. Okay, so in other words, the force passes through the point I take moment about. So look at this right here. If I choose this point right here, this is point A. If I take moment out of this point A, then immediately R, Y, and Rx will disappear in this moment. Okay, Rx and Ry don't create any moment at all because D, this distance, is 0. Okay, and since up here I already determined that Rx is 0, so that's already quite simple to begin with, right? But if I choose this point as the point I take moment about, then I can just eliminate this Ry altogether, right? So just to make it a little easier. Okay, so let's do that. I'm going to make some space here. So equation 3, sum of forces, now about point A equals 0. Okay, so some moment, right, about point A. So look at free body diagram again. Rx, Ry don't care about because they don't create a moment. And before you can actually proceed, you need to define positive as counterclockwise or clockwise. So I'm just going to say clockwise. Okay. So the first moment, okay, is coming from this force. So it's F1 times, let's say, D1. Okay, or D1 is this distance. Okay, and this force about point A would create a clockwise moment, so that's positive. Okay, and then the next moment comes from this W. Again, it's positive, right? So about point A. So W times D2. And D2 is this right here, this distance. Okay, the perpendicular distance. There's a third moment, okay, on the left hand side, which is this right here. And that's exactly the unknown. And since this MA, again, I don't know the direction, I just assume that it goes counterclockwise, so I need to be consistent with that. So minus MA. That's it. So equals 0. Therefore, to move things around, unknown on the left hand side, F1 D1 plus W D2, plug in numbers 1200 times 2 meters plus 981 times 3 meters, right? Half of the length, right? Plug in numbers